So this is the third session of the mini bootcamp, and essentially today we'll be going through details of a transaction to understand what a transaction actually looks like, and then also to start a little bit about smart contracts. And yeah, I'll be making an introduction about smart contracts and to help you understand the language that we're going to be using. So I will begin right away. So these are some of the terminologies that we need to be familiar with for us to be able to move on smoothly in terms of building smart contracts from this point forward. So yeah, and so essentially a smart contract, like I said earlier, it's a program that is built on a blockchain and you can integrate it with a front-end interface for users to interact with it, and then they'll be able to make state changes on the blockchain through your smart contract. Perhaps if they're transferring tokens from their addresses to other addresses, or they're executing some computations that are predefined within your smart contracts functions, they'll be able to do that. They're actually games built on using smart contracts. There's a number of them. I think I could show you one game. So that means they're smart contracts that are running those games that as a player is playing, they're making state changes on the blockchain. Either they're transferring, maybe they're buying, for those that have played games like what's that game called? Minecraft. Games like Minecraft. You're buying assets on chain and you're being able to play with these assets in the game after you've purchased them as NFTs. We're also going to understand what NFTs are. They're like digital assets. So I think the most prevailing use case of NFTs right now is in gaming. They're essentially like digital assets, things you purchase and you can use on chain. And for those that have played games for a long time, we've been buying tokens in gaming environments and using them to play the games and stuff like that. So essentially, that's exactly what happens with NFTs and engaging smart contracts to build tools that you can use in a game. But yeah, we shall start at the very beginning for us to understand the meanings of these words. So, like I was saying, uh, all these terms are very important for us to be able to understand how to build smart contracts efficiently. Yeah, we should be able to interpret these different things when we see them. So, like we talked about these things earlier, an address is just a unique identifier on a blockchain, and it's clearly defined here. So when you when you when you create an account or a wallet on a blockchain, you're given an account with an address. So an address identifies that account and then assigns whatever balances are attached on that account or whatever assets that account has are recognized by that address. So that address is something that looks like this. So it looks something like this. They start with a 0x. Now, Ethereum addresses and all EVM compatible chains have addresses that start with a 0x. And that's the standard of Ethereum addresses. So wherever you see a 0x in blockchain ecosystem, it represents an EVM compatible address, either for an externally owned account or for a smart contract. So even smart contracts have addresses that look closely similar to this. And when we deploy our first smart contract, we're going to see what the address looks like. So yeah, this is the standard of Ethereum addresses. And everywhere you see this in a blockchain ecosystem, it's a hexadecimal number and it represents an Ethereum address. So the address could represent an externally owned account or could represent a smart contract itself. Yeah, and that's what it is. It's an identifier of an account on chain. So it could be an externally owned account, or it could be a wallet address, or rather, a contract address. And then unknowns. I actually put this in the group today. I don't know. I don't know who X is. I just wanted to demonstrate how to transfer value. I have your dollar in USDC, a worth in USDC. Maybe I'll send you more than that, but just wanted to demonstrate it, but I think we'll do that at the end, how we can transfer value between each other. So you'd have to send me your address, then I can transfer that those tokens to your address. But I'll do that at the end. So a nonce is a number that represents a transaction count by address. So what a transaction is, I think I should actually have put it here, but let me just explain it. A transaction is any operation, any activity that changes the state on a blockchain. And we talked about state the other time, and we said state is the status of all the things that are stored on a blockchain at a particular time. So at a particular time, your address has perhaps 2 ETH, and then after you've transferred it to someone else's account, it becomes 0 ETH, or you've transferred perhaps less than 2 ETH, and it will be maybe you transferred 0.5 ETH. So you'll be left with 1.5 ETH, and then 0.5 ETH is transferred to another person's account. So that transfer that changes the status of your account balance, and then also changes the status of another person's account balance is called a state change. It's called a state change, and every operation that does those kinds of things that changes the balances on people's addresses, any operation that also runs functions that change other things other than balances are called transactions. So anything that changes state on a blockchain is called a transaction. So every time you run a transaction from a particular account, whether it's your personal account, your externally owned account, or your contract, there's a counter on your contract or your externally owned account that tracks the number of transactions that you're running. So every time you attempt to make a transaction, that counter will increase will increase in number. So if I sent money right now to someone else, it will show me maybe this is your 12th transaction from this account. And then if I try to send money again, tokens again, the number would be different. It would be like the 13th. The dialogue. You mean this section?
Sorry, I mean, this there's a dialogue that's blocking us from seeing the full screen there. Like your screen is still visible to others. That dialogue there, that pop up.
So yeah. So like I was saying, a nonce. Let me just demonstrate it here as well. It's a number that represents the transaction. It identifies it uniquely, other than the transaction hash, because every transaction has a transaction hash. But other than the transaction hash, every transaction has a different nonce from another. When I attempt to make a transaction, I want to attempt to transfer. I have USD on Celo, Celo rather. I have Celo on Celo, and you can see the balance is 0.08 tokens, Celo tokens. So I'm going to transfer it from one of these accounts to the other, to the test account. When I attempt to transfer this by clicking send, then I choose this address, which is already in my wallet. Just put a value of 0.01. I hope I have that one. Okay, 0.01. Then I click continue. The moment I click continue, my wallet will pop up, will show me this transaction information. And there's a lot of information here. So I'm sending 0.01 Celo, which is worth less than 10 cents. And the network seller produced from this account to that account. And these accounts are given names here because they're in my wallet and they have names. But otherwise, it should show me the address. Even when I click on it, it shows the address of the person of that account here. It is blood. I hope if I remove this name, it will show. But there's an address here. I don't know if you can see it, but there's an address there. So this is just a name that I've assigned to this account in my wallet. So the network fee is this 0.005 Celo. And when we continue down, there's this this value here. You see the nonce? When I point here, it says uh, there's a message it's showing here. Hope you can read it. It says this is the transaction number of an account. Nonce for the first transaction is 0 and it increases in sequential order. So every transaction that you make is counted on that account. So you can tell an account that has been in existence for very long, even before going to the Explorer, or an account that has been active by the nonce number, because every transaction that you do is counted by that account. So this is my second transaction. When I confirm it, it should reduce this value. It has sent some of it to this account. Here you can actually see there's a message that has popped up here asking me to go to check for my notifications. It has reduced the value. Let me see, today's 13th. So I made this transaction just a few seconds ago. And there's so much terminology here, but today we'll be going through it and understanding what it really is. Now, when I check back up here, I don't know why it isn't updating. 0.08. Maybe I sent really little, like it's trying to round off. But yeah, I've sent some tokens to this account, or I sent them somewhere else. I think, yeah, it's right here. 0.01 Celo has been received by this account, by this address. And I'm going to try to do exactly the same operation again. Exactly the same operation again and see what happens. So I'm sending again. I'm going to send exactly the same amount. And when I continue here and I extend downwards, you can see now the nonce reads 3. Then I can confirm this and yeah, the transaction is gone. Now the purpose of the nonce is to avoid replay attacks. So what that means is that if perhaps the transaction hadn't been finalized yet, the transaction I made first, if it has not been finalized yet, and then I make exactly the same transaction again, the EVM will not get confused and maybe assume that this is the same transaction. Or perhaps in instances where there's been some kind of glitch and the first transaction went through, and then the second transaction, or perhaps there's some kind of glitch and the EVM would perhaps recognize a single transaction as two. You get it? There's no possibility of that happening because every transaction has a different nonce. So before it actually verifies if a transaction is valid, those are some of the things that are checked to verify the identity of a transaction. So even if two transactions were exactly the same in terms of the amount that is being sent to another address and the address that they are sending to being exactly the same, they have uh, fundamental differences that don't allow them to be recognized as a single transaction. They have a different nonce, they have a different transaction hash. And all these are security features that were established in the EVM to enable it to be proof against attacks like replay attacks. We'll look at them if we have some time. But yeah, let's continue with the other terms. Okay, so we're looking at a nonce and now a smart contract. So a smart contract, we've been talking about it a lot. It's a self-executing program on a blockchain, and it's immutable in the sense that if you've already built the code, there's nothing you can do about it. You cannot change it. So that's advantageous, but it's also disadvantageous at some level. So you might be wondering, how do smart contracts then get upgraded? If I had some functionality and I wanted to upgrade it, how am I able to do that? So there's a term in the field called proxy contracts. So that means instead of you having to put all your logic in one contract, You enable the functionality, like execution capabilities in one contract, and then you store your results in another contract. So you can always change the contract that does the executions, but it's something we'll look at later. Now, a block like we've defined, I think we did this in the very first session. It's a batch of transactions that have been finalized on a blockchain. Then a consensus mechanism is the mechanism with which transactions are validated. So imagine if like these transactions I just made, for them to be finalized, to be accepted. By the way, if I check the blockchain explorer right now, I can see all those transactions. I could show you. I can see all those transactions. This was confirmed. I can view on the block explorer, and you can see this is a transaction. This is the transaction information. The address the tokens came from. Oh, I was sending to the same address. That's funny. I was just transferring across the same address. I don't know how I made this mistake. But they were going from the same address to this to exactly the same address. I think that's why my balance didn't change. But yeah, so there's 25 here in gas price. So we're going to define what gas price is and see an example of how gas price is calculated as well. So all this information is available on the Explorer because these transactions are being finalized. They've been accepted and my balance has changed. Okay, of course I was sending to the same address, but if I was sending to a different address, the balance would show differently. Show a different balance on mine and different on the other address that I would have sent it to. So every computation that is able to do that kind of change on a blockchain, because your addresses recognize those state changes. Like we looked at the ledger, imagine your address as your name, and then all the other information assigned along with your name that corresponds with your name as your information, your account balances. If you remember the ledger we looked at in the very first session, picture this to be something like that. So your name or your address in this case just identifies you and gives you access to that information to modify it in the sense that you can transfer value from your account to another person's account. So the consensus mechanism is the mechanism or the protocol with which a transaction is finalized or a block is finalized. Think about things like there's a consensus about how many transactions should be in a block, or what things are checked about a transaction before it's finalized. So all the validators, all the nodes that are responsible for validating and finalizing transactions are supposed to take transactions through that process. So like I transferred money from my account to another person's account. Before that value is changed and transferred to that person's account, the validator nodes will check, do I actually have that balance I'm trying to transfer? What is the nonce of the transaction? All that information. What is the gas price that I'm paying for it? Is it sufficient to make the transaction move forward? If it's not sufficient, it will revert the transaction. So uh, those are things that we're going to look at in detail. So a hash, like I said earlier, we actually generated a few hashes earlier. It's a cryptographic fingerprint. It could be like every transaction you make has a transaction signature that confirms that a transaction was done, and the transaction signature has information about the address that made the transaction. So when I check a particular transaction hash, I should be able to tell which account made the transaction and was this transaction actually successful. So everything is verifiable on the blockchain in the sense that you can always whatever is designed to be retrievable from a hash will be retrievable by anyone that knows how to do it. It is open, it is public. And then mining is just the same thing as validation, only that it's specific to the Bitcoin blockchain and all the proof of work systems, proof of work blockchains. But Ethereum uses a proof of stake consensus mechanism. I will go into detail of that, but there's that distinction between those two. So, yeah, I believe that is sufficient. The terminologies we need to know about a transaction. And then the other information I think we really need to know about a transaction are these terms and calculations. So, like I was talking about gas. Now, gas is an arbitrary value that represents computing power. So imagine if you're making a transaction, if you're transferring ETH from your account, from your address to another person's address, there's computation that has to happen for that change to happen, that change of state to happen. And the amount of computing power that is required for that change to happen is measured in gas. It's called gas. But gas units are arbitrary. So when I show you, let me show you something here. When I check my transaction on the Celo Explorer, there's something here called gas price. Let me check for more details. There's something I want to show you. Gas limit. Can you see this one, gas limit? Can you all see it? So what gas limit represents is the amount of computations that are going to be made for that specific transaction to be complete. The amount of computing power measured in gas. So what this means is that you need 21,000 units. You need 21,000 units of gas to make the transaction that I made. And then when I come down here, um, there's something called gas fees. We're going to talk about it in just a moment. Could actually get back to that, but you can see all the information about this transaction is here as well. The nonce is here, the position in the block is there, and so many other things that I won't get in detail of right now. But yeah, I hope that makes sense. Now, to get in a bit of detail about gas and other things about gas, here we have something called gas price. So every single unit of gas, so like you saw on the previous screen, it was showing us 21,000 units of gas. Now, every single unit of gas has a value, and that is called the gas price. So if you have 21,000 units of gas, each unit among those 21,000 units has a value, and it's measured as a gas price. So the gas price, if I wanted to find out the gas fees that I would pay for the transaction, gas fees is the amount of gas or the amount of ether that you will pay for that transaction to complete. I would have to calculate the gas price and multiply it by the gas limit or the gas that I used for the transaction. So if I use 21,000 units, I would have to multiply it by the price of a single gas unit. And that's what is called the gas price. Then the gas limit is, like you saw on the previous screen, a gas limit is just the maximum amount of gas that you can limit your transaction to spend, because it incurs an expenditure in your money, in your token balance. Now, ETH, the native token on the Ethereum blockchain, has three popular denominations. There are so many other smaller denominations, but these are the major ones. And the smallest unit of measuring ETH is called a wei. But a wei is equivalent to 1 power 18 of an ETH. And we shall see this on the next screen. Then a gwei is an equivalent of 1 over 1 to power 9 of an ETH. I know I may not be making so much sense, but let's look at this example. I think I should show this in Paint, be able to understand it more clearly. Just a moment. So when you look here, what I've simply been saying is the one if is a one if is equivalent to this in way 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 18. And that equivalence is because, particularly on the blockchain does not deal with decimals. It deals with only whole numbers, particularly in the Ethereum blockchain. Everything is measured in whole numbers. Every calculation you see, the operations are only in whole numbers. So for you to obtain a decimal from perhaps maybe I sent 0.5 ETH, I have to convert it to the whole number version of it in way. So the equivalent of one ETH, rather one way, if one way was what I was calculating, it would be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So a single way is equivalent to that in ETH. Does that make sense? But the denomination in which an Ethereum, a smaller unit of an Ethereum is measured on the blockchain is converted to the whole number version of it in terms of way. So every single unit of Ethereum on the blockchain is measured in way. And it's simply to cover the issue of them blockchains not using whole rather decimal values. So they had to find a whole number alternative for the decimals in a smaller denomination to represent a single Ethereum or smaller units of an Ethereum. So if I was sending 0.05 Ethereum tokens to someone, the equivalent of it in way 0.05 Ethereum tokens would be this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So as you can see, this is actually a whole number. It's a big number, but if it is in way like that, if it is in way, it is representing smaller units of Ethereum. Does that make sense? Units that are under one ETH. So the representation in way is because blockchains don't use decimals. They don't use decimal values at all. So for them to achieve a value that is smaller than 1 for a single Ethereum, for Ethereum tokens, like if I send 0.5 tokens, and then they are going to be represented in whole number format on the blockchain, then there has to be a smaller value that will account accurately for the value that I have shared in terms of Ethereum. So just like a dollar, a single dollar is represented by 1. But I could just type here 1 US dollar, 1 US dollar. And that represents a single US dollar. You hear that? But how about if someone was trying to send cents? How do we represent that in terms of US dollar? In terms of a US dollar? To preserve the denomination, if I have say cent 70 cents, in terms of a US dollar, that would be something like 0.7 US dollars. See that? But the equivalent of it in cents, which are the smaller whole number denomination of a US dollar, this would be 70 cents. Here, you see that? So what Ethereum does is that it only uses the whole number version of the smaller units of an ETH. It doesn't use the decimal values. So everywhere you're going to see something like perhaps like something like this, like 7 million way. It is a representation of a value in ETH. It's just that this must be smaller than it could actually be a representation of 1 ETH, which would be 1 to the power 18, a single ETH. And if you send someone 2 ETH, it's an equivalent of 2 to power 18 way. Am I making sense? This is very important because when we start making calculations of how much value we're going to be sending in smart contracts, we need to understand this concept. So I'm going to demonstrate it in an example I put in my slide, but I hope you're getting the point. If you're not, you can raise your hand and ask a question. I'll be more than welcome to help clarify it. So if perhaps if I was sending 0.05 ETH to someone, and I divide that by the standard of a single way, I'll type something like this, power 18. So you can see, but this is a multiplication actually. So if I'm multiplying it by the standard of 1 ETH against way, this is the amount I'll be sending to that person in terms of way. So which is 5 with 16 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So when I send someone 0.05 ETH, I'm sending them an equivalent of this amount in way. Now on the blockchain, the amount that is being transferred across in terms of ETH is measured in way. And this is why you're supposed to really know about it, because even when you're measuring gas, the amount of gas that you're going to be spending, you measure it in another denomination that is slightly bigger than a way, but still in a whole number format. Like the example I gave earlier of the US dollar and cents, you can choose to represent a single dollar in cents as well. So a single dollar is 100 cents. The whole number is that. So 100 cents is an equivalent of one whole dollar. Is that right? But how about definitely raise an error? But how about if I wanted to send someone 70 cents? For sending someone 70 cents, this is an equivalent of how much in dollars? This is approximately $0.7, right? So what I've been explaining is in Ethereum, think of this dollar as the ETH, and then the cents as a way, the smaller whole number representation of these smaller units of ETH. So it's like a kilometer and a meter. A kilometer is big, so I could choose to represent smaller units of a kilometer if I was supposed to say perhaps 0.7 kilometers. And instead of representing it as a decimal unit, I represent it in a smaller granular denomination, perhaps which is meters. So 70 kilometers is about, I think, rather 0.7 kilometers is about 700 meters, rather 7,000 meters. Am I right? Yeah. Essentially, that's the same exact concept. It's just that in this case, it shouldn't really confuse you. It's just that the number is big. Comparing an ETH with a way, is much bigger in representation. One ETH is worth quite a lot of way. It's I think a quadrillion. Quadrillion is a very big value. But the amount of a single ETH in terms of way would look like a very big thing, but they're just really small units of ETH measured and written in a denomination that is a whole number, just like I've been demonstrating in distance and what and dollars, between cents and dollars. So that's what a way is. It's the smallest unit of ETH, the very smallest unit of ETH used to measure the amount of ETH that you might be transferring around on a blockchain. So, so now here's a hypothetical example that I want us to look at. So in this example, if we're all following, by this time you should already understand what we're trying to do. We're going to be sending 0.125 ETH, but converting it to Gwei. So we'll look at Gwei. You can ignore that for now. Let's focus on Wei. So you can see 0.125 ETH. When we use this value in terms of Wei to determine the amount of Wei that we're sending to this person, these are 18 zeros. So when you multiply this value by 18, we'll get the equivalent of 0.125 ETH in terms of Wei that we're sending to this person. So this is what the blockchain will recognize. This is what the Ethereum blockchain recognizes. Recognizes the value in Wei. Because this number was too big for people to understand, they had to find an easier expression of it that is easy for people to understand, because honestly, this is much easier to understand than this. This number is intimidating, may make you think you're having a lot of money. Well, of course, 0.125 ETH is not very little money, but this number is really, really misleading. And it would make sense if it just remains in the background, in the computations in the background. And we have this as a representation of that value um, as the value that interfaces with the people. So yes, that is the representation of ETH, this particular amount of ETH in Wei. So we have 0.125 ETH. We multiply it by this, we get the value in Wei that the person was sending. So Alice was sending 0.125 ETH to Bob. And when we see the amount that was sent, it is exactly this amount in Wei, but it's also exactly this amount in Gwei. Now, Gwei is also another denomination of ETH. It's usually used to measure the gas. It's actually designed to measure the gas price rather. So every time you're making a transaction, there's an amount of computations that that transaction requires. And like I said earlier, every transaction has every unit of those computations has a price, and that price is measured in Wei. So to get back to our demonstration here, one ETH is equivalent to this amount in Wei. The point though is an exponent of 18 in Wei. So that's the amount of a single ETH and its equivalence in Wei. But then one ETH is also an equivalent of 1 to power 9 in Gwei. So you can see Gwei is now a bigger representation compared to Wei. Like you need not so many units of Gwei to represent a single ETH than with a Wei. With a Wei, you need a quadrillionth. With a Gwei, you need only a billion. A billion Gwei represents a single ETH. A quadrillionth Wei represents a single ETH. I hope that makes sense. There's a distinction there that I want us to pay attention to. So if I was transferring 0.125 ETH by multiplying by that value, just this more efficient here. So I had 0.125 ETH and I want to convert it to Gwei, I'll have to multiply it by its standard conversion rate of a single ETH in Gwei. Yes, Tracy.
I was asking,
Yes,
are those zeros supposed to be 16 or 18?
they're
Or
18.
wait, 18. Okay,
They're
thank you.
18. A single ETH is one with 18 zeros of Gwei.
Okay, thank you.
So this is 18, and this would be that would be the amount of 0.125 ETH in terms of Wei. So this is I'm going to represent this value with all the zeros. This is 1, 2, 5 with 17 zeros. And I want you to pay very close attention. These are 17 zeros because this is one decimal place less than a whole ETH. So if we did a calculation, this would be something like this. 0.125 times that times this value, like multiplied it here, it will give us this amount. Then if we try to turn it back, if we add 125 along with the 17 zeros, like I'm going to put them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Why there are 17 zeros is because this value is not an equivalent of an ETH. It's one decimal place less than the equivalent of an ETH. So we remove 1 0, meaning it is less in amount than an ETH. So when I divide this by the standard rate, which is 1 exponent 18, it should take me back to this very same value. Says 12.5. This is, did I miss out something? 1 to 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think it's interpreting this other number very differently. But the point is, when you make the calculation, it should take you back to that very number. It's in a different format, I believe, but I can't fix that now. So now Gwei 0.125 ETH. If I want to convert this to Gwei, it is an equivalent of this number multiplied by the standard rate of a Gwei, which would be 0.125 multiplied by 1 exponent 9. Now this is the equivalent of this amount in Gwei. Because the other number was big, it was showing us the exponent instead. Oh, I should have been multiplying earlier, that's why it didn't work. But I think you can make sense of this. This one is more visible. So a single Gwei is worth, let me do this calculation. So a single Gwei divided by the rate of a Gwei against an ETH. Has rounded it off. Let me try to just write it here. 1, 2, 3, 1, 2, 3, 1, 2, 3. So this would be something like my calculator won't be able to calculate it. That's why I'm trying to put it here, but it's still in different formats. But the point is, a single ETH is equal to 1 exponent 9 in Google. And then a single ETH, the very same amount of ETH, is equivalent to 1 exponent 18 in Wei. So this is the smaller denomination, and then this is the larger denomination. This one is usually used in measuring gas. This one is used in measuring the amount of ETH that you're sending across on the network. So this is for the amount of gas that you're paying. Now let's look at an example in our very own transaction here. When you look at this, the gas limit was 21,000. So this means that we use 21,000 21,000 arbitrary units of computing power to execute this transaction of transferring 0.01 ETH, Celo rather, from this address to that address, although it's the same address. I don't know why I was doing that. But you can see that the transaction actually happened. That's the value I was transferring. This is the transaction fee in Celo. Then the gas price is that. So that means for every single unit of gas that I'm going to spend, this is its price. Okay. Now I would multiply this by the 21,000 to get the amount that I actually paid in transaction fees. And you can see this is the value that I paid for each computing unit, each unit of gas. So if I multiply this with the 21,000, I should be able to get this amount, the transaction fee, the actual amount that I paid. So before you get the transaction fee, you need to know two things. You need to know the gas price, the unit for every computing, rather the value for every computing unit, computation unit that you're going to use, and how many units of computation are you going to use. So in this case, we use 21,000 units, arbitrary units of computing power, and each of them costs this amount, which is the gas price. And then when you multiply this by the gas price, it should give you the transaction fees, the amount that you've actually spent on that transaction. So we can try this out. When I copy this, multiply it by 21,000 in, oh, I closed it. I hope it shows. So I have that, and I multiply it by 21,000 units. Okay, it doesn't actually calculate it. The calculator won't be able to show it, so I'm using command line tool. Okay, so I multiply this by 21,000 units, and it gives me this value. It's 0.005250021. Now, when I look at this value, you can see this is exactly the same price that I paid in Celo in terms of transaction fees. So why that is important is as we're running transactions, rather as we're building smart contracts, we need to pay attention to the gas price and the transaction fees. Because every time you deploy a smart contract, you're going to be spending gas. So there are so many things you can do to optimize your smart contract. Make sure it doesn't spend a lot of gas, not just for you as you're deploying, but for also the people that are going to be using your smart contract. So there are certain exchanges, because there are so many dynamics that control the value of a transaction, the value of an exchange that you're trying to make. Maybe if you're transferring ETH to Celo, or you're transferring ETH to Polkadot tokens, those are transactions because they are going to change the value, the balance on your account, and add that balance on a different account. But how much would you pay for that transaction to be executed? There are so many dynamics, but one of the things that you have control over, you as a developer, is how you write your smart contract. Because every transaction that you make, or every transaction that every person that is going to use your smart contract makes, is going to consume an amount of computing power. But some operations consume more computing power than others and actually achieve the same thing. So you need to be able to know how to optimize your smart contract. Like we're going to look at it. So you need to always pay attention to all these details when you're attempting to deploy a smart contract. Think about it. How much is the person going to use in terms of their own tokens just to be able to interact with my smart contract? Now, this is where there's a distinction between traditional programming and Web3 programming. You need to be conscious of how you write your code, specifically for not just this purpose, but for many other reasons. Security is one of them, but gas optimization and gas efficiency is another, and it's really, really important. I wish I could show you different exchanges here and see so that you can see the difference. So the differences in these prices, like I'm going to show you, is not absolutely controlled by gas optimization. There are so many other dynamics, market dynamics, But of course, how the smart contracts that I'm going to be interacting with when I attempt to make these transactions, how they were built is critical to how much money I'll be paying to make these transactions. So I'm going to try to exchange one token for another on different exchanges, and we see the difference in price. I'll try to exchange exactly the same amount. So this one is called PancakeSwap. It's a decentralized exchange. And what we said a decentralized exchange is the platform that allows you to exchange between two different tokens on compatible networks. So I'm going to attempt to swap on PancakeSwap and on Uniswap. So on PancakeSwap, I want to transfer base to Celo perhaps. Here, base. I hope it shows. I may have to connect my wallet first. So on the base network, what tokens am I going to be transferring? I want to transfer ETH on base to ETH on Celo. If I can see that. I don't think I have Celo here, but let me use any other blockchain. Maybe Arbitrum. So on Arbitrum, I still want to receive ETH. So I'm transferring ETH tokens from base to Arbitrum. And perhaps I want to transfer to ETH. So approximately that is 5,000 US dollars. And I'll be receiving 1.999. Of course, there's the transaction fees that will get involved. Even this exchange itself needs to take a cut from this transaction. So that's why I have to receive 1.99974 approximately. Now on Uniswap, I'm going to do exactly the same thing and see what happens. So I'll be transferring from, hope it can show up. I see base here. Maybe I should use the super bridge. Arbitrum and base are both. They are both optimistic roll-ups, so it should be there. Okay, so here I'm going to be transferring ETH from base. So from base, I'm transferring ETH to Arbitrum. Be here. Let me try to find a different bridge. From Telos to ETH. No, from base. So let me transfer from base to ETH directly. I think that will be easier. So I'm transferring ETH from base to Ethereum network. Now there's a difference between a network and a token, between a chain and a token. So a token is a unit of value that can be transferred across the different blockchains. So most of these EVM compatible chains have a representation of the ETH token on those blockchains. So Base has an Ethereum token on Base, Celo has an Ethereum token on Celo, Ethereum has an Ethereum token on the Ethereum network. So all EVM compatible chains, most of them have a representation of Ethereum natively handled by a smart contracts on those blockchains. So that is why here, when I attempt to transfer ETH from Base to Ethereum, and I can choose the token here. So I'll be transferring Ethereum. Like I said, in my previous transaction, I'll be receiving this amount, or it's approximately this. approximately this is the amount that I'll receive of it. So let me change this from base to Ethereum also. No, on Pancake Swap rather. ETH on base to ETH on ETH. Ethereum on Ethereum, not the Arbitrum network. Okay, it's not showing me, but let me use the super bridge and this layer 0 and the super bridge. Let's see the difference. So perhaps I'm transferring from super bridge here. So perhaps I'm transferring from base to ETH, base to ETH. I'm transferring exactly the same amount. Two. This reads I'll be receiving, okay, this is, I'll be receiving approximately 1.99 ETH on this, the super bridge. Then I go to layer 0, this is 1.981. Because it's the same token, why should I be receiving a different amount? There's a number of things that come into play here. All these bridges um, have a different percentage that they take from the transaction, but also the smart contracts that are controlling these transactions play a part in how much I receive, and that's essentially goes down to how did they write the code. There are some operations they could have done which would have done exactly similar things that don't consume a lot of gas, and then others consume more gas than others, but they achieve closely the same thing. So those are things we need to pay attention to, and that is why I really brought out the concept of gas in the definitions. So yeah, I think if you will allow me, I would love to continue and then look at other things. Unless there are questions up to this point about gas, about how the EVM reads numbers, I would love to continue. Are there any questions? Can we go ahead? Does anyone have questions? No one, okay. Can go ahead. Let me check. All right. So to move forward, now down to the programming itself. So we're going to be writing smart contracts, like we've been defining them, in a language called Solidity. And Solidity, just like also many other languages, it's a programming language, and you write code like you write code in any other language. Those of you that are familiar with programming, you've either written code in JavaScript or Python or C or Rust. Well, there are so many languages really designed for different purposes and different execution environments. But specifically for the EVM, there's this language that is popular, particularly in the Ethereum ecosystem. So most blockchains have programming languages that write smart contracts on those blockchains. But generally, Solidity takes the bigger share of the pie because EVM compatible chains are much more compared are much many. There are so many compared to any other kind of blockchain. So layer one compatible chains, layer two scaling solutions like Celo is. There are so many compared to other blockchains that use different consensus mechanisms, that use different execution environments of smart contracts. So most of them are compatible with Solidity. So the way we're going to be writing smart contracts in Celo is the same way we're going to be writing smart contracts on Base, on Ethereum itself, on Lisk, all the blockchains that you've been seeing me demonstrate here. Most of them are all of them are actually EVM compatible. But maybe I could show you some that are not. That would you would have to use a different language for you to build smart contracts on them. A few of them are here. Let me type this. There's so many other kinds of blockchain other than Ethereum. These are the other blockchains that exist, and there are so many. You can write smart contracts on them in their specific implementations of smart contracts implementation languages. So there's one called Cosmos. So for those of you that are familiar with programming from before, this one uses a language called Go. Go was actually written by Google. It's a low-level language. What that means is that closely similar to, oh, I think this is not the website, but it's called Cosmos. I think this is something else, but you can look it up. There is Stellar. Stellar is also an independent blockchain. That's its logo. So this one is written in Rust. The smart contracts are written in Rust. Superbridge has all those blockchains that have their smart contracts compatible with Solidity. Now, all these, as you see them, if you wrote Solidity code like we're going to write it, you can deploy it on any of these blockchains, as you see them here. All these. But particularly, we're going to be writing smart contracts on this one. It's called Celo. But everything as we're going to be doing it on this blockchain, we can do it anywhere else on all these blockchains, just the same way without making any modification. So I think that's the advantage of Solidity. It's really, really scalable in a sense that you can deploy your contracts anywhere and they'll be efficiently accessible and usable. So Uniswap is one of those protocols that has deployed their smart contracts on almost all these blockchains. So they're able to exchange value across all of these ecosystems seamlessly. And these ecosystems now have communication systems enabling them to interact with each other. So if I add tokens on base, perhaps it's easy for me to communicate and send them back to Celo, or even execute smart contracts from base and execute smart contracts on Celo on the Celo blockchain. It's now possible. Previously, it was very complex. All blockchains were existing in independent vacuums, but now there are protocols that enable blockchain ecosystems to communicate, blockchain protocols to communicate with each other. So yeah, and going to be particularly building on Celo. So I'll tell you a little bit about Solidity language and how it's different from so many languages and its power as a programming language. So the Solidity language is a high-level language. By high level, I mean the kind of code that you're going to be writing is closely similar to English compared to some other languages like those that have written any programs in C. C is slightly low level. Like you're going to be writing a lot of symbols that don't make sense in English at all. But Solidity, the advantage of Solidity is that it's representation of concepts, it's representation of instructions. It's closely similar to English. So it's almost like you're going to be writing a variation of English, but not exactly. So it's the language from which smart contracts are interpreted on a blockchain. So when you write your smart contracts in Solidity, they are going to be compiled. Compiling is converting your code into something that is interpreted by the EVM. So typically we've heard of machine code. So machine code is the language that machines understand generally. But a variation of machine code called bytecode is what the Ethereum virtual machine actually interprets. So the Solidity as a language has a very close relations to languages like JavaScript, like Python, in the way instructions are written. So if you have experience writing programs in either of these languages, I think you'll pick up the syntax and the interpretation of instructions much, much faster. And yeah, I think those are most important things about Solidity, perhaps to tell you it's focused on writing smart contracts exclusively, and that also it has an element of being gas sensitive. There's so many instructions that you can write, but most importantly, you need to put in your mind that every time you write an instruction, you're going to be spending gas for as long as that instruction to be for as long as for that instruction to be executed on chain, it is going to make a change in the state on the blockchain. So yeah, I think it's right about the time that we can dive into Solidity. So we're going to be using an IDE. Has anyone been in programming before? Has any of us been in programming before? You could raise your hand, you could unmute and give us your experience or what kinds of things you've been building. Oh, Maria, you could talk to us, please.
Hello?
Hey.
Yeah, I only heard you say that. Okay, you asked that question if anyone has programmed before. Yeah,
Okay.
and
So,
yeah, I have a bit of experience in programming.
mhm,
I've worked with Solidity. Yeah,
okay.
and this is like a recap. Yeah, so basically, programming is using programming languages. Let's say JavaScript, uh, Solidity to come up with a program. Yeah,
Mhm.
or basically it's the execution of programs using a programming language. In this case, which is Solidity.
Okay, yeah, thank you for for that submission. Yeah, well, I think we can now go directly into Solidity. So we've talked about Solidity a little bit, but most of the things about Solidity we'll learn them as we go. Now, we could have used an offline environment to write our smart contracts, but that's a little bit advanced. So we'll start with an online environment, an online IDE, and it has a very particular name. It's called Remix. Actually, I have it here already. So in your browser, you can type, if you're with me, you can type this, Mix Ethereum IDE. Show it for you among the results, your search results. So you can type Remix Ethereum IDE. If anyone is programming with me, you could let me know so that we can move at the same pace. So here is the very first option. I think I should actually share it in the what? In the chat. So this is the site that we're going to be looking at. This is where we'll be building our smart contracts for now. And then later, perhaps next week, we shall look at Hard Hat. It's a more advanced tool and will help us build smart contracts more efficiently. But for purposes of understanding how Solidity operates, we shall be studying here. So it's let me share this link. You can copy it, but I think I'll also put it in the Telegram channel. Yeah, so that's the link we'll be using. So yeah, this is the environment. Excuse me. This is the environment we'll be writing our smart contracts in. It's an online environment, and you don't have to worry about making some downloads and integrations. It is fully sufficient to help you build your smart contracts and deploy them. So I'm going to be building smart contracts and then deploying them on the Celo network, Celo Alpha Just network. But if we want, just that I don't know if any of you have mainnet tokens, you can also build on mainnet. But since it's easy to get testnet tokens, we shall just build on the Celo Alpha Just network. And you can always get tokens from the faucet. I think I shared the faucet link. So all you have to do is get tokens from the faucet because you're going to need tokens for you to deploy a smart contract. And as well, you're going to need tokens to interact with the smart contract if you're running functions. The only computations that don't require you to spend any tokens are the ones that involve you just reading information from the blockchain. Like if I was just seeing someone's balance on their account, I don't need to spend gas for that because I'm not changing anything on the blockchain. I'm just reading something from the blockchain. Now, all those operations that just require you to just read the information on the blockchain, um, they are available for you to just read, and they won't require you to spend any gas. But anything that requires that you change the state of the blockchain, transferring value from someone to somewhere, or you're changing the value of state variables in a smart contract, we shall look at that. All those require that you spend gas, and yeah, you would have to have tokens on your account to be able to make those computations successfully. So here I want us to start from zero, so I will delete all this. I don't think I need it anymore. Uh, so when you open this environment, it starts like this, and there's information here on the side. These are tabs that you'll be using a lot. Then here, your workspace, all your files, the files that you will create will all be here. Then this is just an introductory page, so I'll close it. And yeah, down here you'll see all the operations that you're running, interacting with the blockchain. So I can always minimize this. So when I'm deploying a smart contract, all the information that is happening will show down here. So I'll minimize this up to that point. And then here, just to demonstrate it for you, all these tabs serve different purposes. I don't think I should have this here for now. So the major ones that we'll be using, most of these tabs are going to be very important, but we shall focus on this and this and that. These others we shall use them a little bit later, all these others. But the one that we'll be focusing on is the file explorer, the compiler, and the deploy and run transactions tab. So the very first one, the file explorer, is just where your files are always going to be. So if I created a file, this is the symbol that creates a file. When I click on it, I can give it a name. I can say this is our first contract. Now, Solidity files have an extension, just like you have your music files having extensions of .mp4, .mp3, even a Solidity file. It's recognized by its extension, and the extension is .sol. When you have an extension file, when you have a file with an extension of SOL, that suggests it's a Solidity file. It's a contract file, and inside there we'll be writing Solidity code. So when I press enter, it will attempt to open the file here. So this is how a file, of course, opens, and you can always open other files. These are just support files that will help your smart contract be. They're just really there to support your smart contract, but I think I can actually do away with this. I don't really need it. Now here you can create a file, like I just created a file. This is a contract file. I'll be writing my smart contracts in here. And you can see this is the active file from right up here. And then the search in files, this one just helps you to search your file explorer to see different files that you have, different folders that you have. Like in this case, I have a file called first contract. So when I type in here first contract, it will show me the results of all the files and folders that have exactly that name. Let me just type first. Zero such results. Okay. I don't know why it's doing that, but it's supposed to help me see. Oh yeah, it searches inside the file. Let me just type something here. So instead of that, I just type, and you can see when I type the word pragma, it identifies the file that has that word in it. So every keyword that you put here to be searched is going to be looked for inside the contract files. And when it finds it to show you the result, the file in which that word is existing. So yeah, let me first remove this. Now that's what this part is for. This tab here, the search keyword, the search tab. Then the compiler, like I said earlier, what compilation means is that you're converting the Solidity code that you're writing into a language that is understandable by the EVM called bytecode. And we shall see what bytecode looks like. But why it's important for us to write in Solidity and not write directly in bytecode is because bytecode is difficult to understand. It's closely similar to ones and zeros, and there's so many instructions that it's very difficult for you to uh, master all the instructions that you need to execute a specific smart contract. If you're going to be writing it in bytecode, it will be very difficult to learn it. So that's why most of these codes are transferred into a language that is closely similar to English, so that it's easy for us to know the instructions that we're writing and make it much easier for us to debug our code. And so the compiler, where you see the Solidity compiler tab here, what you're supposed to do when you click here is compile your code. So because the code doesn't have anything meaningful, it has an error. That's why this button is inactive. But we should be able to see it active if our Solidity code has met all the conditions of valid Solidity code. And then when you're done, this is the section where you deploy. When you click here, it should allow you to deploy your smart contracts on a particular blockchain. So in this case, we'll be deploying on Celo, on the Celo testnet, Celo Alpha host. And when you're deploying, here you choose the network that you'll be deploying on. Not actually the network is determined here, but here you choose the environment that you'll be deploying on. Then the address that we'll be deploying. Remember when I said externally owned accounts can have rights over a contract? So a contract is always deployed by a certain address. And that address, you can choose to have exclusive rights over certain functionalities within your smart contract, or leave it open for other people to interact it as freely as you interact with it. But the point is, there will always be an address that deploys a smart contract. And you can choose the address you want to use when you connect your wallet. And then here you can customize the gas limit. So now this is all in amount of GUI. Remember? Then the amount that you'll be sending along with that transaction, we're going to look at those things in detail. So I can write a simple smart contract here that transfers value, the amount that I put here, that transfers an amount of way from maybe an address to this smart contract, the smart contract that I'm going to write. But for you to make sense of it, let's first look at basics of Solidity as a language. But I would love to see if anyone has a question. So yes, we'll be looking at Solidity, and there's a number of things about Solidity that make it special and well suited for building smart contracts. First of all, it's explicit, static, I mean. So for us to be able to build smart contracts in Solidity, there are certain things we need to be aware of about Solidity as a programming language. First and foremost is that it's statically typed. What that means is that when you're writing smart contracts, there are certain things that you're going to be creating certain things are going to be creating. They are called the actual containers, like containers of information. For those that haven't been in programming before, every programming language has these. They're called variables. So variables are just, think of them as containers that are going to be containing information of very specific types. Now, even in programming language, there are types that are predefined by the programming language itself. And these are types, the kinds of information that you can store in these different specific containers. So the kind of information that that container stores is determines the nature of that container. So think about it. If you have a sugar bowl, why is it even called a sugar bowl? It's because it contains sugar. Or why do you have a salt shaker? It's because it contains salt. Or all those kind of containers, they contain that specific um, maybe ingredient or powder. It contains that specific powder, and that is where it derives its name. You hear that? So even each of these containers, they can have specific identifying names, but the nature of these containers is determined by the value, the kind of information they store. So these are the kinds of information that exist in Solidity. They are integers. So as there can be containers for integers, then there are strings. There can be containers for strings. Strings is just text. Think about that message that you type in um, in your WhatsApp message, in your WhatsApp or your Telegram entry what entry forms of information. You can have integers, and integers are just numbers as you know them. Then strings is just text. So think about strings as that information that you enter in your input in WhatsApp or Telegram. It's just text. Even if I put a number there, I would not be able to calculate in that environment because it's not designed for calculating, and it only receives strings. It only receives text. So even if I enter the 9 plus 5 in that string, it would not calculate it. It would just enter it the way it is and recognize it as text. But if I enter the same value in a calculator, it expects me to calculate things. So when I enter 9 plus 5, it should do an enumeration of those numbers. But they have to be in a different form. They have to be in the form of numbers. But if I enter numbers in text, they are recognized as text. And there are specific ways these particular data types are recognized. These specific forms of information are recognized for you to distinguish them. So a number is represented by integers are just represented by numbers. So if I enter the number 98, it would be just that 98. And when I enter a number without any additional quotes around it, okay. And yeah, we're looking at data types, all forms of information. So there's a lot in this language. We may not be able to cover it all through this bootcamp, but I'll give you fundamentals to understand how to build smart contracts. Most of the other things will be in our future engagements, perhaps we'll keep learning them. So data types, these are forms of information, simply forms of information. And I was giving you an example. I said they are integers, and I said these are just numbers. Like I said earlier, Solidity does not deal with decimal points. So it deals with whole numbers alone. So every time you enter a number, it's either going to be an integer or a representation of a value in way. So not every number in Solidity is actually a representation of way. It only becomes a representation of way if you're doing operations that require you to transfer value across, like maybe from one account to another. So otherwise, they're just numbers. And they are represented by every time you see something that is written as a number with no modifications, like perhaps having quotes around it, then it's just a number, recognized as a number. It's enumerable. What that means is that you can do calculations with it. But otherwise, if it has quotes around it, then it's a string. It is just text. You can't calculate with text. The example I gave is for you putting a 9 plus 7 in your WhatsApp text environment. Doesn't calculate it. It just sends the message exactly the same way it is. Doesn't recognize it as a value that can be calculated. So whenever you see a number, anything representing a number written like that, it's just a number. And then a string is just text, and it's represented by quotes. Every time you see something written in quotes, either single quotes or double quotes, it is just a string. It is just text. It is recognized as it is. Okay. Then there are other data types. The other forms of information we have is addresses. So an address is actually an ethereum addresses. Addresses as we've been seeing them. So every time you see something that has a 0x and then some characters up to 42 characters, it is an address. So for example, my wallet will allow me to open it. I hope you can see my screen. I believe you can. This machine is relatively slow, but yeah, I should be able to receive that. To show you an address, I've been showing you addresses anyway, so it won't exactly be a new thing. Password. So that's what an address would look like. Something that has a 0 and X. Now that address could be an address of an externally owned account, like your own account, this one's in my wallet, or a contract account. So contract accounts and externally owned accounts are represented by the same standard of wallet addresses. Starts with a 0x and then characters going forward from that point. Now these addresses are public addresses. For an externally owned account, what we see here in the wallet is a public address. The private key is what we saw in the second session. That number, that very long number, I may not be able to show it now, but yeah, that very long number that you show representing that address. So this particular address that you're going to be interacting with is generated from that private key. Get it? And usually what happens is for you to execute transactions, those activities that change state, that require your specific rights to be able to modify the state on the blockchain, either you're sending someone money or you're calling a function on a smart contract, those are the things that require your private key for signature. Otherwise, everything else is accessible. You can just query it like information that is visible. You remember that day when I was looking at the screen on an Explorer and seeing the balances of the people? All those things that I can see there, I can query them in a smart contract. You get it? And be able to perhaps use computations and whatever I want to do with those values. So I can get someone's address, I can get someone's account balance, I can get a number of things about a particular address, but I can't make changes. Contract interactions, so all these are contract deployments. $5 on this. Okay. So now an address looks like that, and every address will have this same standard. Will look exactly like that. And there's a data type called address that stores addresses. Then we have another type. Actually, these are the most basic. And then everything else is just really data structures. So we have data types and data structures. Integer strings, addresses. Yeah. Now, data structures. We have three major data structures. We have one called an array. So this one stores a set of information, but of the same data type. So imagine something like a container that stores different integers. Maybe I have a number 7 and 4 and 5 inside square brackets. That is what denotes an array. It's represented by square brackets. So wherever you see square brackets, that data structure is called an array. Then we have another called a mapping. The data structure, that means it stores these data types in bundles, they store them in a combination. They are not exactly data types, they are structures in which these data types are stored, instances of these data types. So a mapping looks something like this. It associates two data types. Perhaps I have an integer or a string associated with an address. You get it? Think about that ledger. Remember that ledger? Maybe we have your address. Oh, let me actually do it that way. Let me, instead of having an address, instead of having a string, we have your address and showing your balance. Now your balance has a data type. It's an integer. It's just a number. So it's like if we had a mapping, would be storing perhaps your particular address and your balance, the balance on your account. The balance on your account. Now we have another data type called a structure. That one is represented by curly brackets. But we shall see all these as we keep moving forward. Now we have units in smart contracts that are responsible for handling computations. So when we're trying to send money, when we're trying to send ETH across, we're sending it using functions. There are computing elements that are responsible for transferring that value across. They're called functions. Now these are the basic elements of any programming language. Generally, any programming language has data types, has data structures, and has functions, and so many other different things. But essentially, these are the basics. Then there are special things, small special things under each of these different classes that we can understand for us to be able to build smart contracts efficiently. So I'll start with data types and see how they're exactly written. Now, for those that don't have experience with programming before, there's something called syntax. Syntax is like the grammar with which a language is written, in which a language is written. Think about English. If I wrote something like, are you going home? Perhaps if I was asking a question, say, are you going home? This sounds like a question, right? And someone reads it, but grammatically it's wrong. I mean, if someone read it and they didn't know English, and perhaps they understood the basic grammatical representations of English, then they would know how to interpret it. Is it a question? Is it a statement someone is just saying? So in English, questions are represented with a question mark after the statement. So that is how English is written. And those are the rules that govern how English is written. So every programming language has rules that govern how things are written in that language. So in Solidity, there are specific ways you're supposed to represent a data type. There are specific ways you're supposed to represent a data structure. There are specific ways you're supposed to represent a function. And I will start with data types. So for you to define an instance of a data type, for example, I want to store an integer. Integers are of two types, these data types here. They are unsigned integers and integers. Okay. So we're going to look at these different types of integers. And then under unsigned integers and integers, there are also different kinds of unsigned integers and different kinds of integers depending on the ranges of numbers they store. So for you to know the range of numbers an integer or an unsigned integer type stores, you do the operation of show you the operation. So we have uint 8, we have uint 16, sorry about that. We have uint 32s, these are the standards. We have uint 64, we have uint 128, up to uint 256. So for you to be able to know how to determine which data type you should call your number, you should give your number rather, you need to know these things and the ranges that these numbers store. So they store different ranges, and that's why they have different denominations, different kinds of names. So for you to know the range that a number stores, a particular integer, an unsigned integer stores, you use the operation. It's actually just a formula. 2, it's actually 2 to the power n minus 1. So think about it. If I have a uint 8, the range of numbers that a uint 8 can store is 2 to the power 8 minus 1 on the lower end and also on the upper end. So I would love someone to get me this answer just for us to be actually active. So what's the maximum number a uint 8 can store according to this formula? I'll be waiting. I'm giving it 2 minutes at least. Someone could just unmute and give us the answer to that. The maximum number that a uint 8 can store according to what? According to this formula I just gave us. Yeah, I want you to find me the largest number that uint 8 can store. We shall see how it works. Yeah. Okay, 255. We can verify if it's actually true. So you guys say 255 for a uint 8. So what that means is that a uint 8 excuse me, stores numbers according to that formula. It stores numbers all the way from a 0 to 255. Like that's the maximum range of numbers it can store according to that formula. So this is it. This is how you actually define an instance of a uint 8. First of all, you specify that particular variable. Like I said, a variable is a container that contains a specific value, but it's defined by the name of the value that it stores. The type of the container is defined by the kind of values it's going to store. So first of all, you define the type that it's going to. What kind of data is it going to store? It's going to store a uint 8. That means it's going to store numbers between 0 and 255. And what particular name does it have as a what? As a variable, as a container. So let me put the definition here. Let me put it down here so that it's easy for us to refer to it. So when you're defining variables, you should have this in mind. Variable is data storage unit in a smart contract. Okay, so that's what it is, and this is how you define variables. First of all, you specify the type of the variable, and this type represents the data format it stores. So it might be, for example, uint 8. So that means it's going to store numbers between 0 and 255. What that also means is that if you try to put a number that is out of that range, it will raise an error. Or it could be a uint 16. So perhaps someone could get me the upper limit of a uint 16 using this formula. But first take a moment. Let me explain this, then we come to that. So this is how you start. You define a variable. You start with the type of the variable. The type comes first. And second goes the name of the variable. So the name of the variable could be anything. So you could be saying you're storing a number 45. Okay? But that number 45 is arbitrary. So Jonathan says it's 6, 5. Okay, thank you very much for the calculation. We're going to also verify if this is true. So, like I'm saying now, the name of the variable is what that number actually represents. In this case, if we're storing a number. So you're saying, perhaps you're going to store a 45. And I said a variable is just a container, a data storage unit in a smart contract. So think about that pantry in your home with all those different containers. Each of them is storing something different. So if perhaps you had 3 powders that look closely similar, but for someone to know what kind of powder is in a particular container, you have to label that container with a name. Okay? So what is the name of the variable? Now, the name is just an identifier that identifies that specific variable, that specific data storage unit, and distinguishes it from others. Okay? So let's say, just a moment, please. Okay, so the name of the variable is just an identifier of the data storage unit. So after you've typed the type of that variable, then you type the name. So this is like, what information will it store? What is its name? Think about it. A salt shaker stores salt, but it's called a shaker, a salt shaker. You get the point? The container is called a salt shaker, that's its name, but the type of information, rather, the type of content it stores, it's called salt. So it has a name and also has something that it stores. So when you're defining a variable, like I said, you start with the type. What is it going to store? Then second, what is its name? So the name comes second. Name comes second. And then what it's going to store comes after the equals sign. Now these are called operators. We're going to look at them as well. But since we're going to use it here, let me type it here. Now the operators that serve different purposes. They help you do different things. One that allows you to assign a value. What does assigning mean in English? Can anyone help me define it? Maybe you could just put it in the chat. Anyway, my own understanding of assigning is giving a value to something. I can assign you as my representative. So I have given you the rights and privileges as my representative. So in this case, the assignment operator is the equals sign. When you see an equals sign, a single equals sign, this is not for suggesting that one thing is equivalent to the other. No. It means that you're getting what is on the right, what is going to be put on the right, in this case, which is going to be the number. So what number am I going to put? I'll do 55 perhaps. And then every statement, every single statement in Solidity into the semicolon. So this is a statement, but the information I've entered here is just these are just representations. So in this case, the information I'm storing, what is the type of the information? it's a uint 8. Then what is the name? I could call this upper limit. Okay, there's a reason why there's an error here. We shall look at that later. But this is the way you define a variable in Solidity. You start with the type, the information it's going to store, then the name of the variable, and then after the equals sign, the information, the actual information that it's going to store. Okay? So this equals sign is an assignment operator, and how it works is, the screen may not be very visible. Let me try to zoom in. How it works is, whatever is on the right is stored into the container on the left. Get it? So this is the container. So it gets whatever is on the right and contains it. Whenever you see an equal sign, what is on the right is being contained in what is on the left. Is that clear? Let me get a thumbs up if you're following. Those that don't have developer experience. Okay. If we're all at par, then yeah, we'll just keep moving forward. So those data types. Now, if I was storing a uint 256, I would type this uint 256, then say upper limit. I don't know what the upper limit of 256 is, so I'll need someone to help me calculate it. But we'll start with uint 16. Jonathan helped us with that, and he said it was a 65535. So I would say this is also an upper limit. And then every statement, like I said, now this is an assignment statement. You're assigning one value onto what is on the left. You're assigning one value onto what is on the left. Everywhere you see this equal sign, single equal sign is an assignment operator. Then there are other operators like plus. This is very obvious. It is for calculation, adding two numbers. What is on the left, what is on the right. There's a minus, subtracting what is on the left. Rather, what is on the right from what is on the left. There's a division. Now the division is represented differently. Instead of this symbol that we're very familiar with, where is it? Where is it? I actually don't see it on my keyboard. So, but you know the symbol I'm talking about, the division symbol as we know it, a dot up, then a slash, and then a dot down. Instead of that symbol, we represent it with a forward slash. This represents division in programming. A forward slash represents a division. So this is for division. This is for subtraction. This is for addition. This is for assignment. All these are operators. They serve different purposes, like you can see. The equal sign for that, the plus sign for addition, minus sign for subtraction, the forward slash for division, the double equals sign for comparison. Get it? Double equal sign for comparison. So what this does is that it compares what is on the left to what is on the right. What you're simply asking is, what is on the left, is it the same as what is on the right in terms of if they were evaluated? For example, a 6 plus 2 is it the same as a 7? Yes, it is. Or maybe a 2 plus 1, is it the same as a 3? Yes, it is. So this is used in comparison operations. If you want to compare something from the, if you want to compare what is on the left to what is on the right. And then there is a greater than symbol to compare if what is on the left is less than what is on the right. And I think this is also comparison, but a different kind of comparison. This is comparison, but equality comparison. Then this is greater than comparison. Get that? Greater than comparison, this is greater than. We type it like this. Okay, so I'm going to go to a new line just to help us keep track so we don't get lost. Then there is another symbol which could be the same as a greater than, but it's a greater than or equal to. And we're going to see the differences with all those. So this is also comparison, but it's greater than or equal to. Comparison greater than or equal to. Greater than or. And then we have the opposite of this. So these are all operators that serve different purposes. We have that, which is represents less. It's also a comparison operator, but this one represents less than. What that means is that it compares what is on the left, what is on the right, with the assumption that with the question of is what is on the left smaller than what is on the right. If that is true, then to return a true value. If it's a false, to return a false value. Maybe the other data type I didn't talk about here is a Boolean. So a Boolean is just a true or false value. So anytime you see a true or a false written just like that, now that is not text. They are recognized as a data type, true and false. They're actually a data type. So when you see them written just like that, they are a Boolean value. They represent a true or false result of a computation. So here we have a less than or less than or equals. It's also a comparison operator, but it's less than or equal to 2. Okay, so that's where we are. And I think we've used only one of those, which is the assignment operator here. And like I said, every single statement ends with a semicolon. But there's a reason why there are red lines here, and we're going to see why. Are there any questions up to that point? Oh, Debbie says we talk about enums. I think enums will come in. For those that don't have experience in development, I don't think it would be fair to bring in those things right now. I think we shall talk about those perhaps tomorrow, rather on Monday, so that I give you the weekend to go through Solidity, understand it in detail, and some of these things perhaps practice them like we're going to do this. Like we're going to practice them. So yeah, there are so many other events, other things. I would love to talk about events. I would love to talk about constructors, but it won't make sense to talk about that now. So I want to start with the fundamentals, the absolute fundamentals. So yes, at this point, are there any questions? Any other questions regarding what we've been looking at so far? We can move forward then. So here I was simply defining integers, but then I can also define a string. So if it's a string that I want to have as my data type for a particular variable, simply type the keyword string in case string and the name of the variable in which I want to store this string. Perhaps it's a name. And then, like I said, a string is represented by quotes. So you're supposed to type that data in quotes. Get it? So it could be maybe just type something like that. Anything, as long as it's in quotes, it's recognized as a string. So I could just type my name here, or perhaps the name of, let's say, Celo. So this is a string. It's just represented as text. You can't calculate it. It's simply something you just type. This could be someone's name. Now, other data types, if it's a boolean, just type bool, bool like that, B-O-O-L. Then could say status perhaps. Then here type anything, it's true or false. That's how booleans are written, and they can be only one of two values, either a true or a false. So any other thing would love clarity on, so far from what we've covered? Okay. So moving forward from here, all these data types are written exactly in the same way. The data type, rather all these variables are declared in the same way. The name, or rather the type of the data you'll be storing, the name of the variable, and then the data that you'll be storing in that variable. Yes, so we have other types. I think we've looked at we didn't put an address. So an address is just written like that. Just have the data type, which is address. Say my address, and then the address there. Oh, it's not an address. Just copy this. So I believe with this and this basic understanding, we can start writing something. Okay. We shall look at some of these others in detail. I just wanted to give you an overview. And maybe the other thing I didn't talk about is a function. So a function is a unit of computations. And how a function is written in Solidity is you start with a keyword. Everything that you see in blue here is called a keyword. Everything you see in blue here is a keyword. It's defined by Solidity itself. So and it represents, these represent data types. So this you enter, it could be anything else depending on the range of numbers you want to store. It could be a uint 256 if you want to store a very large number. It could be a uint 16 if you want to store a relatively smaller number like this. And there's a reason why all these numbers, all these ranges exist. Each of these ranges, as you see them, takes an amount of gas fees for it to be stored. Okay, the larger the number, the more the gas fees it requires for a number to be stored. The smaller the number, the smaller the range, like you see the data type here. Smaller the data type, smaller the amount of gas it requires for that number to be stored. So think about it. If perhaps I was tracking people's phone numbers, perhaps if I was tracking people's phone numbers and okay, someone gave me the maximum range of let me see, of a uint. Gives me the maximum range of a uint 64, uint 32, sorry. The purpose I'm doing this is to show you why you need to be mindful of what kind of data types you determine for specific values to be able to optimize for gas. So the maximum value of a uint 32, what it can store at maximum is 429. 429. 4 9 6 7 6. So I want you to think about it. How many characters does this number have? 1 2 3 1 2 3 1 2 3 1. In any country, this is sufficient to store a person's number. Am I right? This is actually a 5. Thank you very much, Jonathan. Yeah, this is actually the size of a phone number, right? So if you're storing phone numbers on on chain in a smart contract, perhaps if this was actually maybe what are you in 32? I could call it a phone number. If I store the phone number, an actual phone number here, and I said 072, that, that's the entire phone number of a person, and then at the end, a statement. This is a number, as you can see. And then if I did this, the exact same thing, store the phone number. If I did that, look at these two variables. They're both storing exactly the same value, but I can assure you they spend at different, well, stored as strings. Yeah, you can store them as strings. I just wanted to demonstrate the concept of, data types and being able to be gas efficient. But you can really store them as strings because you don't really calculate phone numbers. So imagine these two data types, they store completely the same. Actually, it's really the same thing. But because of the data type that they are, this is a UN32 and this is a UN256, they would require a different amount of gas fees for them to be stored. So if a user was perhaps entering their information on your smart contract, then instead of using a UN32 in this case, you used a UN256. There's nothing wrong with that, but think about how much expenses they have to make. And if operations that are gas insensitive like this or being involved in your smart contract, how um, how much gas would they have to spend just to achieve that particular thing they are trying to achieve? Imagine that. So this is why it's very important as you write your smart contracts, pay attention to the data types that you use, the operations that you're going to request, and how exactly do they impact gas usage of the user, even you yourself when you're deploying the contract. You know. So yeah, I think that's a clear demonstration of gas sensitivity. So I was giving an example of each of these data types as you have them. An array is written like, I think we've looked at most of them, the basic ones. Then I was talking about a function. So a function, like I said, it's a unit of computations, okay? And inside that unit of computations, you can really put anything. Maybe you want to add two numbers together, and you can call that function maybe addition. So the syntax of writing a function is that it starts with a function keyword, then the function name, then these parentheses. Well, this is how the function receives data. Perhaps if you want to enter if a user has entered some information, some numbers you want to calculate, this is how the function would receive them. If perhaps it was an addition function. So the name of the function comes after the function keyword. Then where that function receives the information that it's going to use for the computation it's going to do. Then in the brackets, these curly brackets, you put the computations. Get it? It doesn't matter whether you put the computations on a different line, as long as you're within the scope of the what? The scope of these curly brackets. So this is where it receives data. This is where it receives data. And that data has a specific name. They're called parameters. Okay. Then computations are done on those parameters. Like maybe I had two numbers that I wanted to add, number one and then a number two. I put them through here and then they are computed here in the curly brackets. Okay. So this is how you define a function. And when you're defining a function, what you put in this space, inside this space where it receives data, are placeholders for the data it's going to receive. Okay? Not the actual data, but the placeholders for the data it's going to receive. How you enter the data into the function is when you call the function. Think about a TV. Until you turn it on, it will not work. Okay? It will stay there and screen will be black. Maybe it's powered in, but until you turn it on, it does not work. So that's the same thing with a function. When you're defining it here, it's like you're just creating something. Think about putting a motorbike together, maybe assembling it. That is what you'd be doing here. You're just assembling a function. Okay? When you're assembling a motorbike, there are things that you're going to put together. You're going to put together the fuel tank, maybe the tires put together. But until you sit on that bike and ignite it, it does not run. Until you fill it with fuel, it does not run. So think about the information that this function is receiving as fuel. When it receives the fuel, then it does what it's supposed to do. Makes the computations using that fuel. It runs using that fuel. The fuel goes through the engine, does what it's supposed to do, then the car or the motorbike can run. So in the same way, what I'm doing here is simply defining a function, simply defining what it should, what information it should receive, what it should do to that information. Then I give it a name. Bikes have names. Those who love bikes, you know the names of bikes. So it must have a name, and what defines it? What is it exactly? It's a function. So the definition of whatever it is that you're doing has to always come first in Solidity or in any other language that uses the similar syntax. So if you're defining a variable, data type comes first, then the name. If you're defining a function, the function keyword comes first, then the name. Then what data will it receive and what will it do to that information? Maybe other computations around that are not really related to the data it has received. But if it receives any data, it receives that data from here. And also when it's receiving data, it has to receive data in specific formats. So those specific formats are exactly the same formats that we defined up here. So what data is it going to receive? Maybe it's going to receive a string. Okay. And what's the string name? Placeholder. What I'm putting here is not the data itself, just a placeholder. Just like when you're creating a tank, you're not creating it with fuel inside. Just creating the tank, a placeholder for where fuel will be. Does that make sense? So I can give it a name, maybe say it's going to be the name. Or perhaps let me use numbers. Perhaps I want to do something like a calculation. So maybe I want to calculate a unit 8, which is going to be number 1 or digit 1. These are all just placeholders. Int, another int 8, which is going to be 2. So then I do the computations here inside the function. And I would say maybe I want to multiply the digit 1 by the digit 2. Okay, I think the symbol I forgot to put here is the multiplication symbol. So multiplication in programming is represented by a star. Everywhere you see a star, whatever is on the left is being multiplied with what is on the right. So this is a digit 2. Okay? So think about it this way. Imagine that bike that I'm using the analogy of the bike because it has I think the most appropriate example. So when fuel goes through the tank, it goes to the engine and does whatever it does in the engine. You know, helps run the pistons and then propel the bike forward. But then when the engine was being made, all the pipelines for where the fuel will pass and how it's going to be controlled were just designed. So in the same sense, when I'm creating this, these digit 1 and digit 2 are just placeholders. Eventually, when I call this function, or when I activate this function, actually activate would be a very appropriate word, but it's actually called invocation or calling. When I activate this function, the data that I'm going to pass in here is the data that is going to do these computations to. So this is how I would call a function. Just type the function name, then you put these curly brackets, and then you pass in the information to fill these placeholders. Okay, so maybe this is 2 and use a comma. So I'm receiving only 2 data types. What? 2 variables, rather information of 2 types. One is a uint8, another is also a uint8. And there are 2 digits. So there's 2 and 3. So when I call this function, and like I said, every statement ends with a semicolon. Even this ends with a semicolon. So this would result into an operation of adding a 2 to the 3. Because the digit 1 has, the placeholder of digit 1 has been replaced with a 2. When I call this function by its name, and this name can be anything. Perhaps I want this function to be called addition. So even here, I'll change the function name to addition. Okay. Now, the placeholders that were defined when this function was being defined are now being replaced with actual data. So there's a 2 will replace that, and the 3 will replace that. Then what was digit 1? Take that position. Then what was digit 2? Will take that position. So in this case, when I call this function and pass in this information, I want it to add the 2, which is the digit 1, and the 3, rather multiply them. So this would be a 6. And it's a statement, so it ends with a semicolon. So up to that point, are there any questions for those that don't have developer experience? And with this is a fundamental. This is fundamental for programmers, and we're going to be using it to build smart contracts. Okay. Any questions, or can we move forward? So I'm going to build a basic smart contract. Let me actually think about it. So what would you prefer? Should we build a basic smart contract that just does simple mathematical operations, or should we write a smart contract that allows you to transfer your ETH from your account to another person's account? Like maybe think about it as a protocol. Like if you are sending to follow anywhere in the world, anywhere, these remittance services. If you sent money through them, what they would do is they reduce a percentage from that money, then return, and then send to the person, to the receiver, an amount that is deducted. So we could do something like that. We could build a smart contract that someone can put in a contract address of the person they want to send money to, and then when it goes through our smart contract, it reduces it to a certain level, then sends the balance to the person that is supposed to receive it. We could do that, or we could do a simple mathematical operations. With all this information, we already have enough to create something like that.
Hello?
Yeah, I can hear you.
Yeah, I'm choosing the protocol in mind.
False. those that agree with her, those that are in concurrence with her, you could just raise your hands or give me a thumbs up. So yeah, we can. Since there's no feedback, I'll go with what Tracy has said. And yeah, maybe I should put this should put this code somewhere. You can refer to it for those that require fundamentals. You can go through this, but we're going to actually be referring to it. So let me create another file and name it. I'm going to give it a very appropriate name. Call it the bank. The bank.so. So so for us to write Solidity contracts, there are a few basic things that we're supposed to start with to be able to write a smart contract in Solidity, in Remix, or generally anywhere that you're going to write your smart contract. And that's one of the reasons why these things are raising errors. So you see a red line here. Okay, yeah, so this is what we're going to do. There are two things that you're supposed to start with, basically. There's Solidity is open source, first of all. You need to understand that it's open source as in the sense that all the code is visible to anyone that wants to see it. But there are certain rights and restrictions on how that code is supposed to be used, depending on who wrote the code, depending on the rights that you chose to reserve that code with, and liability you have according to that code. By that I mean, if someone else reused your code and somehow their protocols were compromised, there are certain rights and privileges that free you from any responsibility of you being the original owner or writer of that code. And you need to declare them when you're writing your smart contracts to free yourself from any liability of if someone tried to copy your code, any responsibility of them being manipulated or someone compromised coming back to you in any way. So it's actually a requirement in Solidity that you clearly define under what license are you writing this code. So there's this very open license among all of them. Writing Solidity code has a number of licenses. The people that maintain it, the people that create all new versions, have certain privileges that are assigned to the code and the versions that they create. So the one that is most open source, that means that if someone really, really needed to reuse your protocol, they're using it uh, fully under their own responsibility. If somehow they maybe forget to implement something or they changed something in your code, it doesn't come back to you as a developer of that code. It is fully their responsibility. It is fully their um, liability if anything goes wrong. So the most open, first of all, for you to be able to define the license, you need to type this word SPTX, license identifier. Just a moment. License identifier. Then you specify the license that you're going to be operating under when you're writing this code. So the MIT is the most open source. MIT license is the most open source. And so that simply means that anytime someone chooses to reuse your code, it's entirely up to them. It's open source. Most of this code is open source. There's no way you can even hide it because for as long as you deploy it and verify your contract, anyone that chooses to see the contracts that your address has deployed will be able to see your very specific contract. Okay. And then the other thing, type the word pragma and then the Solidity version. So what pragma is a command that specifically instructs the compiler, the Solidity compiler. So there are so many other pragma commands, but this is the most common. I'll show you all the others later, but this is the most common that defines the specific compiler version that you want to use to compile your code. So every compiler version has some new features that it adds to Solidity to give it more capabilities. And this is why the EVM itself, the Ethereum virtual machine, keeps being upgraded. New opcodes are added for specific reasons, maybe to optimize for security, to optimize for gas efficiency, or to just add new features and make it more scalable, you know. But when these modifications are made, when these upgrades are made, the smart contract languages that are used to write smart contracts for the EVM now start to lag behind in capabilities to build efficient smart contracts for those, or even to build compatible smart contracts at all for those new versions of the Ethereum virtual machine. So what happens is, even the languages keep being upgraded, but also the languages keep, the Solidity language itself keeps being upgraded for different reasons. For it to be more efficient, to have more functionalities, to be able to leverage more capabilities of the EVM. So the upgrades that keep going on both ends, the EVM and the Solidity language itself. But specific versions of Solidity have specific methods with which, rather, ways in which they compile the Solidity code into bytecode. Some functionalities are not compatible with older versions of Solidity. So if there's a way I could write this code, and if I used an older version of a compiler, it wouldn't be able to decode it, rather to encode it into bytecode, to convert it into bytecode, because some of the functions I will be using were defined in higher versions of Solidity. Does that make sense? So when you're writing your smart contract, you need to be very explicit to specify the compiler range, that you can specify a range or a specific compiler version that you want to use to compile your Solidity code into bytecode. So that's what this command does. It specifically instructs the compiler to use this specific version of itself. You know what I'm saying? It's like telling the compiler, please choose the version of yourself that is 0.8.25, because it's the one that is capable of accurately compiling the code that I'm going to write. But although most of these major changes, these major upgrades, don't have very much breaking changes in the upgrades. So that means if I chose a range that is still within 0.8, all these other smaller changes are compatible with any other version of 0.8 in upgrades. So I could choose a range. If you want to choose a range, you simply put the caret symbol. So the caret symbol represents any other version above 0.8.25 can compile this code. So what I'm saying is if the active version is either 0.8.25 or higher, it's okay. Those are the versions that I want to use to compile my code. Okay. So then, like I said, every statement ends with a colon. So that's a colon. And whenever you see a red line anywhere in programming, it suggests there's an error. And this one is telling me there's an error. Pragma, this is actually not right. Solidity. Why am I writing solidity? So yeah, that's the command, pragma solidity 0.8.25. And every time you write code correctly, you can choose to come here and compile it. I chose to auto compile, that's why you see it's compiling, and it compiled successfully. Show you a green tick, but I'll untick it. so that I can manually come and compile myself. But I prefer to it to be on auto compilation so that I don't have to always come and manually click this button of compile. So yeah, now these are the fundamentals. Like you need to always have these in your program before you start doing anything. You need to define the license identifier, like which license are you going to be operating under when you write this contract, and then the version of the compiler you want to use to compile your code. So you can always see the compiler that you'll be using when you come to the compiler tab. So you can see the active compiler is 0.8.26. This one fits within the range that we chose for the compilers that we want to compile our code. 0.8.26. I could choose anything higher than that. Even 0.8.25 would work. And it would attempt to compile because I chose auto compile. So I changed the Solidity compiler version. And like I said, a compiler is a tool that converts your code into bytecode. And bytecode, I said, is a variation of machine code. It's a language that allows the EVM to understand the instructions that you wrote in your Solidity code. Yes, to take a while, but as it does that, we could just simply go back. Let me take it to something higher, perhaps 0.8.28. So when you're done with that, when you're done putting these two statements, the next thing you should do is declare a contract like that. So we're going to be creating a contract. Okay? Then the contract has to have a name, just like anything else. So like I said, everything that you define in Solidity starts with the type of what you're defining, then the name of what you're defining. So we call this the bank. And when you're done typing the name, curly brackets like that. Now all your code is going to be put inside here. All your Solidity code is going to be put inside these brackets. So you can enter and then start typing. Okay, so these are the instructions. So whenever you see two forward slashes, this represents a comment, and it's not compiled in itself. It is just a statement that helps you build faster, build more efficiently. But they're not instructions themselves. They're not Solidity instructions themselves. They're just comments, just statements that are not recognized by the EVM at all. They're just supposed to guide you. They're just guides. So first of all, what do we want? We want to, one, have the user, the person that is going to be sending money. So we're going to have the user send maybe ETH tokens or Celo tokens. In this case, since we're going to be deploying on Celo, I want to send Celo tokens to the contract. And by the way, I think one thing I didn't talk about is just like your externally owned account can hold tokens, even a smart contract can hold tokens. And we're going to see it. So the user can send Celo tokens to the contract, and then this happens. The contract deducts a percentage of the sent tokens, and then third sends balance to the what? The recipient. So from this, my assumption would be that first of all, I need the user enter the recipient's address, right? I need the user to enter the recipient's address, and when they enter the recipient's address, they also enter an amount they are sending to the recipient, right? And after that, the contract will do its job. So this is what I want the user to do. This is what I expect the user to do. I expect the user to do this. Then I expect the contract to do this. These are the contract's instructions. They're just simple. Should deduct the percentage, then send the balance to the recipient, right? Okay, so I think these are the requirements for our contract. So there are a few things that we need to define now. So I want two functions, first of all, that are going to help me with these operations. I want a function for sending balance. And maybe another function for receiving contract. Receiving what? Receiving Celo. Maybe I could call this second function sending Celo. Okay, those are two functions that I need. So the one that receives Celo does the calculation. Okay, and the one that sends Celo simply sends the amount that has been left. Or maybe I could have a specific function for calculating the profits for the contract, or for me, the user. Then I should have another function for withdrawing the profits, right? Because I think this is one thing that many developers forget, and they end up leaving money in contracts and there's nothing they can do about it. Like I said, smart contracts are immutable. If you don't explicitly define the rules for how you want it to run before you deploy it, when you deploy it, there's nothing you can do about it. It's immutable and it's on chain. There's nothing you can do about it. You can't change any code. It will operate the way it was deployed to operate. Then a function for withdrawing. I'm going to run very fast because I see our time is running fast. We have a very short time left. So function withdrawing for withdrawing the. If you have any questions, you can raise your hand and ask. But I'm going to be going fast because I want us to see this work before we close this session. So I think these are the four functions I might need. And yeah, could do that. We could just start. So first of all, I'm going to, this is inside my contract, by the way. This is all inside my contract. But for me to enable clarity of vision, remove it, put it outside the contract so that we can see the contract in its full scope. So this is up, and these are just comments. They don't really mean anything in terms of, they don't affect our code in any way. They're just statements to guide us. And they all have forward slashes, two forward slashes before them. So I'm going to define those functions here. And first of all, I will define the state variables, and we shall talk about some of these details maybe later. So I'm going to define the variables that are going to store the information I want from the user. So what do I want from the user? I want an address for recipient, right? There are more efficient ways to do this. I'm just doing it in a way that I believe it's fast and just to help us see it. So I want this from the user, so I won't give it a value. And I will explain all these other things later. I want it to be public so I can see it. I'll explain all these later, but you can still do some research on them. Visibility modifiers. Want an address from the user. Yeah, I think that's it. I may not even need this here, just have it as a function. So I'm going to define all the functions that I need first. I have a function for receive Celo. These are visibility modifiers, we shall look at them. Okay, so this one takes in an address, recipient, and an amount. We went to 56. Okay. So now this amount has to be in a way. You remember what I said? Yeah, Victor, I could use a mapping. You're right. I could use a mapping, but I want to keep it this as simple as possible for those that don't have experience at all. And then we can do all those things. What do you think? Can we continue or? Okay. All right, so this function is for receiving. Then the second function for maybe calculating profits. I don't need this anywhere, so it can be. Don't need to be like. So don't worry about this, we shall understand it with time. Okay. So I have two functions, one for receiving Celo, the other for calculating the profits. See what value it takes in. Another for sending Celo, another for withdrawing. Let me start with one for withdraw. Withdrawing my profits, me the person that deployed the contract. Wow. Just leave it there. Don't need anything. And then the fourth function perhaps for receiving Celo, right? Oh, they have receiving Celo, then sending Celo. Function for Celo. Don't even need that. So yeah. I think these functions are enough. And we're going to put the logic in these functions, then we will deploy our smart contract, okay? Oh, yes. Okay, so we have four functions, and I'm going to do very specific things. So this is how I would write it. When I receive Celo, actually, let me put this here. I want to put them in an order that is logical for us to understand. So when I receive Celo, I want to calculate the profits, deduct my profits, and then send Celo. Okay? Oh, yeah, it's payable. So, and then send Celo to the person that is supposed to receive the Celo. So this one also takes in an address. That's all it needs to take in. Actually, yeah, the address and maybe the amount. The address of the recipient and then the amount, right? So let's define the logic one by one. So calculating the profits. Calculating the profits requires what? That we get the amount which has been received, apply our operations on it, and then return a result. Okay. So we said how much should we take from this person? Maybe 3%. What do you guys think? Give me a thumbs up. Is that fair enough? Okay. This is maybe received amount. All right. Thanks. Received amount. So when when we receive that amount, we do our calculation on it. So first of all, we're going to put it in an internal variable. But yeah, I'm trying to go fast. So to show you something that works, then later we'll start to understand it slowly. So let's say our profits. Our profits are going to be calculated. And we said 3%, right? So like I said, 3 over 100 multiplied by the received amount. What's this? Oh, I think my mind is just dead, but it's okay. Into 56. Okay. So I'm going to try and make this calculation faster and see that we can come to a conclusion faster. Just a moment here in the profits. 31 minutes. Shall we finish? So what is our rate? Our rate is maybe 3 divided by 100. What you going to this? Okay, maybe let's do this. Mm, yeah, Deborah, I hear you. I do hear you. Maybe we should reduce a specific amount. Do those calculations later. I think my head is just int. So maybe we're storing the rate. And we're going to be taking u into 56. Even this is a u into 56. So this is what we're going to be doing. So we're going to take the rate and want it to be a specific amount of whey, perhaps. Maybe I want to reduce, let's say, very little amount of whey, maybe 10,000 whey, or say a million whey. A million whey is very little money. So I want us to just to be able to see it for every transaction. Every transaction that we make from this address. There are so many ways I could optimize this and make it more robust, but just want us to finish. So I'm going to define, I'm going to define what? A variable here to store the amount that we're going to receive for every transaction we attempt to make. So we'll be reducing 10,000 way from this person, and received amount, subtract. Or this is maybe the one they should send. I could call it to send. Send. We say the received amount minus the rate, right? So first of all, it comes to the contract, and when it gets there, uh, this computation is done. Calculating profits, amount to send. Maybe I should call this amount to send, because after it has reduced that amount, this is the one I wanted to send, the one that I put here. I will say to send, changing the function name now. Then I want you to return that very amount to send. Okay, so we have to, that's why it will send. Let me just change this to a capital T and also this to a capital T. So yeah, we have now one function fully defined, and what it does is it gets the amount that we have received, reduces it by a million way, and then sends the balance. So over time, we're going to be able to see that our contract will be accumulating value. Okay, we'll be accumulating a balance as it keeps sending the reduced amount to the recipient. So we're going to call these functions inside of the functions. So when we receive Celo, this function has to be payable. So when we receive Celo, this function will be responsible for that. When we receive Celo, what do we want to do? We want to store the value of what we have received. So actually, this should perhaps come below sending Celo. Okay, and I will explain why. So the first function is done, and just to define what this function does, this function calculates the amount of Celo to deduct and chooses what to send and return what to send to the recipient. Okay, and then sending Celo, we shall do this. Let's first start with this. So when we receive Celo, what should we do? When we receive Celo, we should do one specific thing. First of all, one specific thing, we should first calculate the amount that we should reduce from that amount that we received. So maybe to specify, to say amount to send. So every function that returns something returns it as data. So when I call this function to send and pass in the amount that I've received here, I expect it to return for me the amount it's going to send. So all these functions are now being called inside receiving Celo. So when I receive Celo, what should I do? Let's calculate the amount to send. That means deduct already. Deduct how much you should send. Then what the second is sending Celo. I just want this one to be called. Okay, it's going to be sent by my smart contract, and it's going to be sent to the recipient as I passed it here as a parameter. Recipient and send what amount? The amount to send, the one that I have reduced. I think already making money, guys. So then withdraw function, this one will be mine. the one who withdraws my profits, only me. This one will be sending to that person. So how do we send? How do we actually send tokens? There's so many ways we can send tokens, but particularly this address has to be payable itself. You have to make an address payable for you to be able to receive tokens. Now, so what are we going to say? Recipient has to receive the tokens. Okay. Transfer. And then the amount that you want to transfer. So what would be that amount? Sending to this person. So the amount will be, I'd prefer that it's this year, so it would be that. Okay, I know some might not be following, but this is as simple as this. Yeah, and then for me to withdraw, I'm going to define a specific variable here for me. And I call myself the owner of the contract. Shall understand some of these things later. Don't worry about that. Shall understand them later. So since I want to assign myself the rights, I need to be in the constructor and then assign owner. Yeah, if you have any questions, you can still just text, okay? Do not. So here I'm calling only one function. Owner. Owner does what? Owner receives what amount? What is on this address? Whatever I want to, whatever the balance is on this address, I just take out. Okay, it's that simple. Send and transfer only available. Okay, only available. Oh, this isn't payable. Sorry, I forgot. Refresh. This payable. What did I miss? Make this payable, I think, as well. It's the only thing that is left. Should be public as well. Okay, I'll just use a function to help me see that. Sorry if I'm moving without saying a word. It's just I want us to see something functional first, then we can think about how to understand these. Don't worry about this. Shall understand it. But yeah, this is essentially me writing a smart contract that is going to do a specific thing. Okay. On a function. So yeah, this is it. And it's not gas efficient. I am going to modify this in another deployment. So first of all, we're going to deploy it here. I'm going to deploy it on Celo. I don't know if I have Celo on this particular address. Celo Alpha Jos. So ladies and gentlemen, we are finally going to deploy a smart contract. See how it's deployed. So Solidity is one of the most widely used smart contract programming languages. And if you want to be a proficient smart contracts engineer, I would recommend you at least start with Solidity. Then you can embrace other languages like Rust. Rust is really wonderful, but it's not starter friendly. So this would be a wonderful start. And it's not so many people can actually write smart contracts. So still give you an upper hand. I don't have Celo Alpha just here, so I think I will just import it when it finishes to compile here. So right now it's attempting to compile. It's actually compiling rather. So I'm going to show you a few tips of optimization, gas optimization. Then we'll close. After it has worked the first time, then we make a few changes, then we can close. So right now it's compiling, taking a while, but it's definitely about to finish. I think there's an issue with my internet today. It's just slow, but should be able to do this the moment it's done. I don't know what should we do because I think there's an issue with the internet. It's really slow, and we've already exhausted our time. So I don't know, should we wait for it or can I just have it in the recording and you guys see it in the recording? I'll share this code on GitHub. Any recommendations on what we should do? But I really hope that this could work. So okay, I'll push it to GitHub, then I'll share the. Perhaps you could actually test it on your own end. As it's failing, and I believe everyone is really exhausted. So, all right, I think yeah, we can close it here. So when it compiles, maybe we can find it in the recording of this very session. And yeah, have a wonderful evening, everyone. Let's resume on Monday with a more robust project. Perhaps we should even integrate it with the, with the front end.